Okay. Sorry, I had to cancel the class on Monday. There were some personal things that I had to attend to. And so your homework is going to be due next Monday, right? Next Monday, yeah. If you haven't, it was supposed to be due today, right? Tonight, actually. So it's going to be due next Monday. What we are going to do is that we are going to go over the Otto cycle and also the diesel cycle as well as the Brayton cycle. And then we will solve an example of the Otto cycle on Monday, right? And then we'll be done with the cycle analysis, the thermodynamic part of the class, and we move on to the propulsion part of the class. Okay? Any questions so far? And I received a couple of emails about this this bonus thing that you were supposed to. I mean, you were encouraged to submit to replace one of your homework, and I guess I explained everything in the email. So if you have a question about that, you can send me an email if you need more clarification. And also that I don't remember if we set a deadline for it. Did we? No. There was no. Let's make it. Let's set a deadline for it. Let's set a deadline. Let's make it due next Wednesday. Okay. Because I don't want to keep receiving these reports throughout the semester. Right? One here, one there. Right. If you want to submit them, it is not going to take you more than like 2-3 hours, or let's say 5 hours to figure this out. We already have a mathematical proof for something that I'm not really clear about yet, but it means that you will receive the bonus points, right? As far as I'm concerned, but I need a report on it, right? It's just a written thing. And yeah, any questions? I will also post your homework too on. Let me actually. It was supposed to be posted today, but we had to postpone everything. I'm sorry about it. Hopefully we can get back on track. Yes.
I think it was the third, fourth lecture that wasn't posted. Is that just the Rankine cycle? I guess the lecture before this one.
The lecture before this one was we had a small discussion on the
Before that.
Rankine cycle then. Yeah. So this is your syllabus. I'm pretty sure you have gone over this. You know this through and through. But your homework was supposed to be posted. Oh, it was supposed to be posted Monday, so you are on the right track when it comes to homework. It will be posted on Monday. It will be due next Monday, and the Monday after. It will be due in a week, and it will essentially cover whatever we are going to discuss on Monday and Wednesday, and also the Monday that is due. So very simple propulsion ideas. Any questions so far? No? What happened to this? Yeah. Okay, let's begin the analysis on the gas cycles. We have gone over the introduction of those. We talked about the different types of gas turbines, different types of jets, the bypass engines, the scramjets, the ramjets, all of those things. You already have an assignment, a bonus assignment on those. So hopefully we are already familiar with the concept. We are going to do a little bit of mathematical analysis today. We are mainly focused on 3 different cycles today. The Otto cycle, which is the regular internal combustion engine, the diesel cycle, which is the diesel engines, is used in diesel engine. We talked about these a little bit. Some of you mentioned the differences and why those differences exist between these two. We are actually going to see what are the differences in the cycle between the two. And then we are going to talk about the Brighton cycles, which are the cycles that are used in jet engine design. Okay. So let's start with the Otto cycle. For the Otto cycle analysis, and for most of the analysis here, we are going to use air. Air is the working fluid, but we are going to assume air is an ideal gas. And we are going to, this part is actually the more important part. We are going to replace combustion process for the Otto cycle specifically with just an instant heat transfer. So heat is transferred instantly to the system, right? So we don't really analyze any combustion here. And there is no exhaust and intake processes. And all of the processes here are internally reversible. We also have an addition to this, all of these assumptions. And this additional assumption is called the cold air assumption. So in some cases, we are going to have this cold air assumption. Not always, but in some cases, we are going to have these cold air assumptions, which essentially, it's a very simple assumption. It essentially means that Cp is independent of temperature. So we're going to use a constant Cp for our analysis. Let's do a small review of the formulas we are going to use for these analysis. First one is the ideal gas law. Who can tell me what was the equation, the main equation? Yes. PV is equals to, in aerospace or in mechanical engineering, we usually use a specific volume and RT, or we use real volume and MRT. And the reason is we don't really use the universal gas constant. We use a specific gas constant. In this case, it's air. And we also had the definitions of internal energy and enthalpy. Internal energy at state 2, and these states are identified by their respective temperatures, is going to be equal to the integral of the changes in internal energy, integral of T1 to T2 CV dt. This is for internal energy. And also enthalpy difference between station 1 and station 2 is going to be the integral of T1 to T2 Cp dt. So if we apply this cold air assumption, we can actually move the Cp and Cv out of the integrals and take the integral. It is going to be a very simple integral. And if you were to use a variable, a specific heat, you can actually use a lot of this. Yes. That's C of V. That's the heat capacity at the. Is this what you are referring to? This V here is a subscript. It stands for the fact that this C, this specific heat, is measured during a constant volume process. Okay? The same is true for Cp. That's C of P. Okay? Yes? Yes, exactly. That's the idea. That's the assumption, right? So we can actually move the Cp and Cv out of the integral. Heat capacity in general is constant. It doesn't change with temperature. That's the cold gas assumption. But if this heat capacity, if we could not use the cold air assumption, it is going to mean that we are going to have variable heat capacity. This variable heat capacity, you can use a host of resources to actually find the relationship between heat capacity and temperature, right? One of the more famous ones is the NIST or NIST webbook. That is, I have referred to this in the lectures. I'm not sure if you're familiar with the NIST webbook though. Are you guys familiar with this? It's essentially a computerized thermodynamic table, right? And it's a very complicated. You can just search for this NIST. You can go to the website. You have to. It's a little. It has a learning curve, so you have to play with it a little bit. But there's nothing scientific to the table itself. It's just you have to understand how to read the data entries and all of those things, right? No, it's very useful. You can actually get all of the careful data from this NIST webbook. Okay, so let's move on with the equation reminders. The other equation we want to talk about is the entropy change. Entropy at T2 and V2 minus entropy at the during station 1, T1 and V1 is equals to, we had two equations for it if you recall. One was the integral of T1 to T2, Cv of T dt divided by T plus R natural log of V2 divided by V1. And also the other equation is a pressure-based equation. Okay. So what will happen to these equations if we can assume Cp and Cv don't change with temperature? Let's make the assumption. What will happen to this equation? And this is a question for the class. So we have these two main equations for entropy change, right? My question is, what will happen to these equations if we can safely assume that Cp and Cv do not change with temperature? We should take them out of the integral, right? So it is going to be Cv integral of dt over t. And what is the solution to that integral? Natural log, exactly. So this delta S, I'm going to use delta S instead of this because it's easier. It's going to be Cv natural log of T2 divided by T1 plus R, bless you, V2 divided by V1, or it's going to be Cp, and again this is C of V, C of T, that's a subscript. Natural log of T2 divided by T1 minus R natural log of T2 divided by T1. Okay, so what will happen to these equations for isentropic compression and expansion? Exactly. Since it is isentropic, is adiabatic reversible, and the reversible part is telling us that the delta S is going to be equals to 0. So 0 CV, I'm not gonna, and we are already assuming that it is cold air. All of this is going to be equal to 0 after this assumption. Okay. So CV natural log of T2 divided by T1 is going to be equal to negative R natural log of V2 divided by V1. The same is true for the second equation. Cp natural log of T2 divided by T1 is going to be, this time it's going to be positive R P2 divided by P1. What can we do with these equations? Can we make any further modifications to them? Or can we simplify them a little more? What can we do with them? How would that simplify things, or how would that give us new information? Let me actually direct you in the, can we move this inside the natural log? These factors, can we move them inside the natural log? We have to split up. And we raise it to the power, exactly. So we're gonna have natural log of T2 divided by T1 to the power CV is going to be equal to natural log of V2 divided by V1 to the power negative 1, negative R. Same is true for the second equation. P2 divided by P1 to the power CP, natural log of P2 divided by P1 to the power positive R. Since these parts of natural logs are supposed to be, so since all of the natural log is equal to each other, these parts also has to be equal to each other, so we can actually say T2 divided by T1 to the power CV is equals to V2 to the power V1 to the power negative R. And also the same is true for pressure equation. Okay, so what is the relationship between R and CP and CV? Does anyone remember this? R, if you recall, we define R as CP minus CV, right? So let's do that here. CP minus CV, there's a negative sign here, so it's going to be CV minus CP, right? And we're going to move this to the other side. So T2 divided by T1 is going to be equal to V2. I'm going to make a little more simplifications here. It's going to be 1 minus CP divided by CV. And this one is going to be T2 divided by P1. 1 minus CV divided by CP. Right? Okay. What does this represent? Gamma, right? Or in this thermodynamic book uses K, but we are going to use gamma. That's the ratio between the specific hits. For what is this value for air? Does anyone remember? 1.4. Exactly. And this is the value we mostly are going to use in propulsion. This value also changes with temperature, but just for simplicity, we use gamma of 1.4. But this part of so if you go through the lectures, you're going to see K instead of gamma. And these are the isentropic relationships, right? You can actually relate pressure and volume as well. Pressure is going to be equal to volume. V2, P2 divided by P1 is V2 divided by V1 to the power negative K, or negative gamma. So second part of the class, starting next week, we are going to use gamma. We're not going to use K. The reason I'm using K is because the thermodynamics book uses K. Okay? Any questions? Have you seen these before? Is this something you've seen before? Way back in thermal. Yeah. So these are the isentropic relationships, right? And these are the relationships we are going to use a lot. The reason I focused on them is because I wanted to make sure that you understand that these relationships only apply to an isentropic case, right? And we also have already assumed that we have already made the assumption that we have cold air, meaning that CP doesn't really change with a temperature, right? So if any of those assumptions were incorrect, you can't really use isentropic relationships. Right? This is something that you have to keep in mind. Any questions? Yes. Sure. Yeah, so R is Cp minus Cv, negative R is Cv minus Cp, right? I'm going to give you a minute to write whatever you're writing, and then we are going to move on to the Otto cycle itself.
So the main equations we will actually use is the bottom one with those movement.
Yeah. And what is the relationship between a specific volume, and this is a specific volume, so what is the relationship between a specific volume and density? You have to speak up, guys. Be a little more confident. A specific volume is 1 over density, right? So we can actually write these equations for density as well. And density is the term we use more in thermodynamic analysis, in mechanical engineering. Yes?
Can we just notate the CV over CP as inverse K?
What's that?
Can we notate the CV over CP as inverse K of gamma?
It is inverse K, yeah. Yeah, I didn't simplify this. It's just going to be 1 over K or 1 over gamma. Okay. Let's actually still give you a minute. So let's move on to the Otto cycle. And we are already the cycle itself. Let's move on to the cycle itself. This is the most uncomfortable desk ever. Otto cycle. So let's actually draw the PV diagram and also the TS diagram. For the PV diagram, we are going to start at 1, go to a 2 during an isentropic compression. So this is where your airflow mixture has already entered the cylinder, right? And you're compressing it. And then the next step is going to go from 2 to 3. This is a constant volume process, right? So constant volume heat transfer. This is where the combustion happens, but the idea was we are going to replace combustion with just a regular simple heat transfer. And then the next process, and these are not straight lines. Just keep in mind, 1 and 2 are curved, right? Because this is an isentropic process. Then we are going to go through from 3 to 4, doing another isentropic. This time, this is after the combustion, so the piston is moving down. We are expanding, isentropic expansion. And then the last one is going to be the heat removal or heat rejection, constant volume heat rejection. Okay. So on a TS diagram, 1 to 2, isentropic, S doesn't change. Then we have constant volume heat rejection from 2 to 3. Another isentropic from 3 to 4, and so on and so forth. We also have, in some books, including ours, we have a 2' and 3' states that we are not going to discuss. So you don't really need to worry yourself with them, but if you were interested in the thermodynamic analysis, I'm pretty sure you can find a good textbook on this that are going to help with the understanding of these prime conditions. But it's mostly related to the combustion that we are not including. Okay? So, as far as we are concerned, these are the 4 states of an Otto cycle. Okay? So, during the compression, we of course are going to have some work. How can we calculate the work here? That's the work from 1 to 2 divided by m. The difference in the internal energies. Like for the Otto cycle and diesel cycle, we mostly use internal energy, unlike the Rankine cycle. But for a Brayton cycle, we are going to use enthalpy, right? So we're going to go back to enthalpy. And for the most of the class, we are going to use enthalpy, because for most of the class, we are going to use a Brayton cycle. Okay? And that's the 1 to 2. Then we have the heat transfer 2 to 3, or combustion that we are going to assume is just a regular heat transfer. And we have the Q from 2 to 3 divided by M is U3 minus U2. Then we have expansion W324 divided by M is U3 minus U4, and then we have the heat rejection. Four to 1 is going to be U4 minus U1. Yes. U3 minus U4. The reason is we want to keep the sign positive, right? But in general, we are losing some energy, right? So essentially it has to be a negative value. That's compression is U2 minus U1. Does this look like a tree?
I think I just accidentally wrote the line.
My handwriting is not a very good handwriting, so make sure there's worse. Who? Odell. Is mine that bad?
No,
I hear a lot of bad things about his handwriting.
it's terrible.
You know you're being recorded, right? I mean. Okay, so how can we calculate net work of the cycle? work 3, 4 minus work 1, 2. Why would you do 3, 4 minus 1, 2? Exactly, it is energy being delivered to the surrounding, right? And this is what we are looking for. So, and we can actually use this U3 minus U4 and minus U2 minus U1, right? What about the thermal efficiency of the cycle? How can we calculate the thermal efficiency of the cycle? Network over Qn, which essentially means that is going to be W3, 4 divided by M, W1, 2 divided by M, divided by Q2, 3 divided by M. And all of these M's actually get cancelled out, so we can actually remove them. This will be the definition of efficiency of the cycle. So, and the reason I asked this was I wanted to make sure that you remember that efficiency of a cycle is the net work of it divided by the energy input, right? So how much net work you are getting out of the energy you're putting in. And that's going to be the efficiency of the cycle. Can we actually use the Q's, use the heat transfers to calculate the net work of the cycle? Yes, we have one. So what is the equation? Q23 divided by M again minus Q41 divided by M. And the reason is, what is the reason? Why can we use this equation instead of the work equation? Conservation of energy, exactly. So this amount of energy has to be equal to whatever heat input is and whatever heat that is rejected from the system, whatever waste energy we have, right? Okay. Any questions here? Whenever it comes to gas cycles, right, we have something that we need to always be aware of, and that's the compression of that gas, right? We are going to compress the air here, right? We have a compression, we have an expansion. The same is true for all of the gas cycles. So that compression ratio is actually a very important factor when it comes to this gas cycle analysis, right? How do we define the compression ratio for the Otto cycle? Just based on definition. The volume at stage 4 divided by the volume at the stage 3. So at the stage 3, supposedly, we have the most compressed state of the cycle, right? And at stage 3, actually, this volume is going to be similar to stage 2, right? And this state. So the most compressed, the most decompressed, or most expanded state divided by the most compressed state is going to give you the compression ratio. Q41. Let me zoom in a little bit. I think it's going to get. Let me make this. Okay. How can I change the size here? I think this is going to be better, yeah. Okay, so the compression ratio, this is actually can be, we can use V2 and V1 for this as well. So V1 over V2 is going to be equal to R as well, mainly because of this. V1 and V4 are the same, V2 and V3 are the same. Okay? And we can use this ratio to rewrite the isentropic equations. So for this cycle, if I want to find the temperature ratio, using the compression ratio, we already had this equation. What is going on here? I don't want to see. We already had this equation. T4 divided by T3 is V4 divided by V3 to the power 1 minus K, right? And V4 divided by V3 is defined as the compression ratio. So we can actually have this. Or 1 minus R, K minus 1, doesn't really matter. And we can also do this for the T2 divided by T1, which is going to give us the same thing, just in reverse. So T4 divided by T3 is going to be 1 over R, K minus 1. T2 divided by T1 is going to be R to the power K minus 1. Okay? What will happen to these two equations if you just multiply them by each other? And I'm specifically talking about 1 over R. This is K minus 1, right? Yeah. Just multiply the two equations by, multiply the two equations and tell me what happens to do this. Okay, let's start from Nicholas and then go by one by one. I want to multiply the two equations. What will happen to the equation and what can I conclude from this operation? There are two equations, right? One, this is equation 1, this is equation 2. I want to multiply them together. What will happen to this equation? The answer can be you don't know. That's all right. The reason I'm going one by one is because I have a feeling that you guys are falling asleep, which is, of course. Okay? Exactly. I guess we have to stop at the question. What's that? T4 over T3 multiplied by T2 over T1 is equal to 1, right? Which essentially means that T4 over T3 is equals to T1 over T2, right? That's it. Is everyone awake? If you want to fall asleep, we can all go home and sleep in our beds, right? So, and I mean, you know me, I don't really have any problem with finishing the class earlier than the supposed time. Okay, we can actually rewrite all of the efficiency equations based on the compression ratio. Just plug in the formulas you already have, and we can actually simplify the efficiency to 1 minus T1 divided by T2, which can also mean that eta is equals to 1 minus r to the power k minus 1. Okay. There's a long way between this equation and this equation, right? And this actually is proved in the lecture notes. But since I want to make sure that you understand how we get from there to here, we are going to have a bonus point here. So prove or get from this equation, eta W net divided by Q in to this equation. One over R, the compression ratio, to the power K minus 1. Okay, any questions? And this will give you, if you submit this by Monday, it will give you 1 bonus point, which is worth 0.5% of your final grade. Okay, this is always the dilemma for access. Bonus points are 0.5%, unless I tell you it is like worth a homework, right? Okay, so let's move on. This is all of the analysis we want to do for the Otto cycle. Let's move on to the diesel cycle. And this is also the air standard diesel cycle. We talked about the differences between the regular internal combustion engine or Otto cycles and the diesel cycles, right? Well, what do you think the differences are when it comes to the cycle, the processes that are involved in the cycle? Like for the Otto cycle, we had a constant volume or an isentropic compression, right? And a constant volume heat transfer, isentropic expansion, and then a heat rejection, right? This part essentially means that when you compress your air completely, there will be a spark, and all of the fluid, the assumption we are making is all of the fluid is going to burn instantly, right? All of the air fuel mixture, whatever, is going to burn instantly. That's from 2 to 0. And during that combustion process, there is no volume change. So it will combust, and then the next process will start, which is going to be the isentropic expansion. But if you recall from last week, what did we say was one of the main differences? There is no, so what does it mean? It's just a straight compression. It's just a, so what will happen to the air fuel mix? Why do you need the fuel then? Because if there's no, the fuel is not going to combust by itself. You need a spark, right? In theory, it will combust, but in reality, it doesn't, right? Gas ignites by itself.
And then this heats up to a point where it ignites. It gets to the vapor. It's like that it basically will.
You actually, you both of you refer to the, are moving in the right direction. The idea is in the gas, in the diesel engine or diesel cycle, what happens is it will take longer for the air fuel mixture to combust, right? Because of the nature of the fuel, because of the design, whatever, right? Because of whatever that is. It will take a little bit longer, right? Which means that we have already started the expansion process, right? So this process here we don't have this process by design. What do we have that is going to replace this? It's actually going to be, based on the design, is going to be an isobaric process, the heat transfer. And what is an isobaric process? It is essentially a constant pressure. So instead of having a constant volume like this, we are going to have a constant pressure process, during which we are going to have some expansion and also heat addition, right? And that the exhaust part is going to stay constant volume. So this is still isentropic. This is going to be isobaric. This is constant volume. This is isentropic. So what does it mean? Everything else is the same. Constant volume, everything else is the same, and we should be able to calculate, use all of the equations we have already had for this analysis. But when we say we have an isobaric expansion, what does it mean for the work and also the internal energy, all of those things? It essentially means that we have heat addition as well as work, right? In the previous process, it was constant volume. There was no work being done by the system or on the system. Doesn't matter, right? So we could have just used the Q for the system. But here, we definitely need to include in the 2 to 3 process, in the heat addition process, we need to include the work that is being done or the volume change, right? So let's actually, and the total heat is going to be affected. So the work that is being done in this process is going to be the integral from 2 to 3 of P dV, right, which is equals to P2 V3 minus V2. Okay? And the changes in internal energy in general is going to be M multiplied by U3 minus U2, right? That in this process, 2 to 3. And based on first law, all of this is going to be equal to Q in that process, the heat transfer, heat addition in this process, minus the work that is being done by the system. So M U3 minus U2 is going to be equal to Q 223 minus P2 V3 minus V2. And if you rewrite this, I guess if you and this is divided by M, so this is also divided by M. If you rearrange this, what you're going to get is Q is going to be equal to U3 minus U2 minus P2 plus P2 V3 minus V2. Okay? Let's actually put all of the 3's together. So U3 minus P2 V3. And keep in mind that 2 to 3 is an isobaric process. So P2 and P3 are the same. Minus U2, this is a plus. Plus P2 V2. What does these two remind you of? This is essentially the definition of enthalpy. So for a diesel cycle, unlike an Otto cycle, your heat addition is actually going to be H3 minus H2. The enthalpy at station 3, state 3, minus the enthalpy at state 2. Everything else is going to remain the same. And we also didn't talk about the TS diagram. the TS diagram, your temperature, the temperature rise between station 1 and 2 is going to, the temperature change is going to be higher than the temperature change, temperature decrease between 3 and 4. So it is not going to be exactly the same as the Otto cycle. It's going to be a little different. This is an isobaric process, pressure constant. This is an iso volume process, volume constant. Okay? So how can we calculate the W naught net or W of cycle? We can use the work input and output of the system, or we can use the Q's. Doesn't really matter. The efficiency we can calculate as W net divided by Q in, which is going to be equal to 1 minus U4. I mean, if you do that simplification, if you simplify, if you like plug in the equations, you will get to this eventually. Right? Or, okay, let's actually talk about this. So how can we calculate the W of cycle using the work in our system? Instead of Q. Here we calculate it using Q, we have the enthalpy, we have the all of the things that we need to have. How can we calculate this using W? We have 3 different works that is being done on the system or by the system, right? One is from 2 to 3, which wasn't there before in the Otto cycle. The other one is from 3 to 4, and the other one, the last one, is from 1 to 2. It's going to be, this is going to be your W cycle. So we can actually put this inside here and use this W cycle for the efficiency calculations. Here? Yes. What's that?
Where does the W3 come in? Like, how does, what part of the process does that happen? SMR.
How do you calculate work? Think of the equation. Isobaric doesn't mean no work is being done, right? What was the equation that we use to calculate in general? Look at this. What was the equation? This is the general equation we use for work, right? So whenever you have volume change, you are either doing work or a work is being done on you, or I mean on this cycle. Okay. We can actually do the same thing. I'm just going to give you the equations here. I'm not going to go over them. Let's give you one definition and a couple of equations. We have the cutoff ratio. That's the ratio at which we decide that we are at the state 3, and then we are going to move to the other process. So there is a cutoff value for this, right? After which this isentropic process starts, right? Because we already are having expansion, and the expansion doesn't stop, it just continues, right? There is a cutoff value that is going to tell us that the pressure is going to change, right? Which means that we are going to go from 2 to 3 to 3 to 4, right? And that cutoff ratio is defined as, by the volume. R of C is defined as V3 divided by V2, which is going to be equal to T3 divided by T2. Okay. We still have the compression ratio, the same as before. So your isentropic relationship for a diesel cycle is going to be like this: V2 divided by 1 minus K, which means that is going to be R to the power K minus 1. And we also have T4 divided by T3, which we can actually use the cutoff ratio and the compression ratio here, RC divided by 1. So based on this, your eta, or efficiency of the diesel cycle, is going to be equal to 1 divided by R to the power K minus 1. This part of it is exactly the same as the previous part, but then we have the cutoff ratio to the power K minus 1 divided by K multiplied by RC minus 1. And this is also getting from the regular definition of efficiency to this is also another bonus point. And again, it is included in the lectures. Lectures are uploaded. You just have to go there and copy this, right? Very easy, yes.
It's RC minus 1, RC raised to K minus 1.
Yes. Okay, let's talk about the gas turbines. I'm moving a little quickly here to make sure that we are covering everything. Gas turbines, or the Brighton cycles, are essentially the things that we are going to focus on, right, in this course. As I have said many times, gas turbines are usually comprised of a compressor, then you have your process 1 coming in air comes in a compressor, and then it goes to the combustor where you inject fuel, right? So this is called a combustor or combustion chamber. It doesn't really matter. And then this goes to a turbine. And from the turbine, you are going to have the exhaust gas. Turbine is always connected to the combustor using a shaft. So some part of the work generated by the turbine is going to be used by the combustor, by the compressor, to compress the air, the incoming air. Okay, that's the idea here. This is called an open loop Brighton cycle. Okay. We can also have a closed loop Brighton cycle in which a heat exchanger I think we talked a little bit about heat exchangers, so you understand what heat exchangers are, right? You don't need to do any analysis. As long as you understand what they are, should be fine. I mean, you should have learned this in Term 1, but okay. So this can be a closed loop or an open loop. We are in propulsion. We mostly deal with open loop Brighton cycle because the thrust generated is a very important factor for us, right? So open loop is going to be the way to go. Let's see. The analysis here is exactly the same as before. As long as you understand one cycle analysis, you will be able to understand all of the cycle analysis. The work is in the turbine, W of T is H3 minus H4, and this is state 3. State 1, state 2. The work in the compressor is H2 minus H1. The combustor heat addition, which we usually use Q dot in for, is going to be H3 minus H2. And the heat rejection, which is Q dot out divided by M dot, is H4 minus H1. Cycle efficiency, same idea. W dot of turbine minus W dot of compressor divided by Q dot in divided by M dot. You just plug in all of the values. This is what you are going to get. Okay. Let's talk about the TS and PV diagrams here for a regular ideal Brighton cycle. We are going to go from state 1 to a state 2 through an isentropic process. So constant entropy, and then we'll go through an isobaric process from a station 2 to a station 3, then another isentropic process, a station 3 to a station 4, and then the exhaust will go back. Your TS diagram is going to look like this. 1 to 2. Here in the Brighton cycle, unlike the Otto cycle and the diesel engine cycle, when the compression ratio was the key factor, we have the pressure ratio as a very important factor here, as a very important definition. And pressure ratio is going to be P2 divided by P1 in a Brighton cycle, which essentially this is the same as saying P3 divided by P4, right? Because of this isobaric processes. So you see the difference between the Otto cycle, the diesel cycle, and the Brighton cycle. It essentially comes down to this process. In Otto cycle, both of them were isovolume. In a diesel cycle, one of them was a combined, is an isobaric. We also have the combined, and we're going to show an example of a combined cycle in the next lecture. Is there any questions? Yes. Sure. Let's see. There are a couple of things that I really didn't go over, like a couple of explanations or like what are the limits. I definitely recommend going through the lecture yourself and reading over those. I'm pretty sure you will be able to figure them out. And let me actually give you the relationship between the efficiency and the compression ratio, or the pressure ratio. In a let me give you this equation as well. It's going to be P1, P2 to the power K minus 1 divided by K. P2, P1, so yeah. So there are a couple of explanations that we didn't really talk about, or yes?
That efficiency factor tie in at all with Oswald's efficiency factor, or are they entirely like
How can you relate this to Oswald?
I don't know.
You are talking about the aerodynamic, the wing efficiency factor, right? How can this be related?
You know, there's a efficiency factor like tied to single prop airplane stuff. More so tied to the engine than the actual.
No, okay, so there are millions of different types of efficiencies when it comes to a design of a car or an aircraft. Doesn't really matter what it is, or even a power plant, right? You have the engine efficiency, you have the combustor efficiency, you have the compression efficiency, also you have the wing efficiency. There are a lot of things, right? Eventually, you have to come up with an overall efficiency, right, that will include all of these efficiencies. Okay? So, let me see. On Monday, what we are going to do is that we are going to solve an example, which is essentially a quiz. So it will go towards your attendance grade. And also, we are going to talk about the modifications we can make to the gas turbine. And then on Wednesday, we are going to move to the propulsion part of the class. Any questions? No? Okay. See you next week.